In this video, we will continue our discussions on truth conditions of logical connectives, truth tables, tautologies, contingent and contradictory sentences, and logical equivalences. One thing to note is that the truth conditions of a conditional statement or a horseshoe sentence in our logical language the same principles of entailment that we discussed in module number 2. In order to see that, first let's introduce some vocabulary. I want to introduce the terms antecedent and consequent. The antecedent is the part in a conditional statement that comes after the if and before the then. So take this sentence: if Bob lives in Riverside, then Bob lives in California. The component part Bob lives in Riverside, this is the antecedent of the conditional statement. The consequent of a conditional statement is the part that comes after the then. So in this sentence, Bob lives in California is the consequent of the conditional statement. Obviously, if this were a horseshoe and we represented, let's say Bob lives in California with R, and then we have horseshoe, Bob lives in California with C, then R would be the antecedent and C would be the consequent. So we can say that a conditional statement like if Bob lives in Riverside, then Bob lives in California is true whenever the antecedent entails the consequent. If the antecedent does not entail the consequent, then the conditional statement is false. And that is exactly what is represented in this truth table. So the only time that a conditional statement is false is under the conditions that the antecedent is true, here P, and the consequent is false. And that's what we have here. These are the truth conditions that indicate that the antecedent would not entail or does not entail the consequent. Any other combination of truth conditions does maintain the entailment conditions of the conditional statement. So I hope that helps to clarify why any combination of truth conditions, except for when the antecedent is true and the consequent is false, do we always get true for a conditional statement and only false for this. So a few words about truth tables. Truth tables represent the truth conditions of complex sentences like these by showing all of the possible truth values of the complex sentence given all of the possible combinations of its atomic or simple component sentences. What this means, for example, is that take a sentence like P and Q. A sentence like P and Q is going to be true whenever its component parts are both true. So here, whenever P is true and Q is true. If either of its component parts is false, then the entire sentence is false. So in a truth table, we represent the main truth value of the sentence by putting that truth value based on the combinations right underneath the main connective. And this becomes useful whenever we're trying to evaluate the truth values of any complex sentence. So every sentence has a particular truth value, and we can use our knowledge of the truth conditions of the main connectives in addition to these truth tables to figure out the truth values of all of these sentences. So consider the sentence, if A, then not A. What are the possible truth values of the sentence given whenever A is true? Well, whenever A is true, and here we represent true, we put T under each instance of A, we're going to know that if A is true, then not A is going to be false. So we put an F right under the tilde here. So now, whenever we have a true antecedent and a false consequent, the entire sentence becomes false. So whenever A is true, the sentence A horseshoe not A is going to be false. And that's why we put the false under the horseshoe here. Whenever A is false, so here we have false under A and false under A, we know that not A is going to be true. So we know, according to the truth conditions of the horseshoe, that if the antecedent is false and the consequent is true, the entire thing is true. So now, by using a truth table, we are able to represent and understand the possible truth values of a sentence of this form given its various combinations of truth values. So again, whenever A is true, A horseshoe not A is going to be false, and here we've showed the work. Whenever A is false, A horseshoe not A is going to be true, and here we show the work. And we can do the exact same for the sentences. So let's start from the beginning. If I ask you to construct a truth table for any sentence, the first thing you need to do is determine how many sentence letters do we have. Well, here, if I give you a sentence B or not A, there are only 2 sentence letters. The next thing you need to figure out is how many rows do we need to have? Well, the basic rule is the following. If you have 1 sentence letter, then you are going to do 2 to the power 1, which means you only need 2 rows. That's why we only have 2 rows here, because there are only 2 combinations for each sentence letter. If you have 2 sentence letters, as we have here, then you are going to need 4 rows. Why? Because we're going to do 2 to the power of n. In this case, n is 2 because we have 2 sentence letters, and so we're going to need 4 rows. And so here we have every possible combination of truth values for these 2. The next thing you do is you want to transfer the truth values that you have put under these sentences under the atomic sentences you find in the complex sentence. So for instance, here A, we gave truth values T, T, F, F. So you want to transfer that and put those same 2 truth values under A over here. For B, we have T, F, T, F. So you want to transfer that and put that under B here. What you want to do next is work backwards to get the truth value of the sentence not A. So we know that if A is true, then not A has to be false. Similarly, if A is true, not A is false. If A is false, not A is true. And if A is false, not A is true. So you want these truth values right underneath the tilde because this is going to represent the truth values for the sentence not A. Now that we have the truth values for B and not A, we can work backwards again, knowing the truth conditions of the wedge to determine what would be the truth conditions whenever B is true and F is false. Well, whenever B is true and F is false, B wedge not A will be true. Whenever B is false and not A is false, then B wedge not A will be false. Whenever B is true and not A is true, then the entire sentence will be true. And over here, you see how the entire sentence will be true. So this column right here, right underneath the main connective, the wedge, represents the truth values for this sentence given these interpretations of their atomic sentences. So now we know what will make this sentence true and the sentence false under the various interpretations here, and so this truth table provides us with that information. Now let's build a truth table for this sentence here. Again, we transfer the truth conditions that we have provided for A to all of the instances of A. There's only 1 instance of A here, so we transfer that here, and we transfer the truth values of all the instances of B likewise over here, and that's what we have done here. So that's our initial step. Ultimately, we want to determine what the truth value of this complex sentence is. So what we really need is to determine the truth value of the horseshoe. We already have the truth value of the antecedent here because we only have 1 sentence letter, namely B. So we need to determine the truth value of this complex sentence by working backwards. So the complex sentence here is not A and B. So let's work backwards. We first need to figure out what the truth value of A and B is. Well, since we know that whenever A and B are true, the entire sentence is going to be true, we put true here. Whenever any of these is false, then the truth value will be false. And that's why we have false all the way out here, because here we have instances of false where either A or B is false or both are false. Now that we know the truth values of A and B, given these various different combinations of truth values, we work to not A and B. So whenever A and B are true, not A and B is going to be false. Whenever A and B is false, like it's all right here, then not A and B is going to be true. So now that we have the truth values for the antecedent represented right here and the consequent represented right here, we have all the information that we need to get the final truth value of the conditional sentence, which will give us the truth value for this sentence under the various interpretations. Again, to figure this out, you just have to know what the truth conditions of the horseshoe are, and you know that the horseshoe is going to be true whenever the antecedent is false or the consequent is true. So the only time that the horseshoe is going to be false is whenever the antecedent is true and the consequent is false. That's what we have here. So we have false. For every other combination, we'll have true. And so right here in this column, highlighted in bold, you see that this is going to be the truth conditions, or these are the truth conditions for this complex sentence under these various interpretations or assignments of truth values for its atomic or simple sentence letter. So here are three important properties of any sentence in our logical system, or what we call a WOOF. If the final column row of a truth table is all trues, all T's, we call that a tautology. That means that sentence can never be false. It's always going to be true under every interpretation. If the final column of a truth table has all F's, that means that that sentence is contradictory because there is no possible interpretation in which that sentence is true. If we have a combination of truth and false, that means that that sentence is a contingent sentence because sometimes it turns out to be true under some interpretations, and sometimes it turns out to be false under different interpretations. Finally, we can use truth tables to determine which sentences are what we call logically equivalent. So two sentences are logically equivalent whenever the last row on their main connectives is identical to each other. So for example, take these sentences. If not B, then A, and B or A. These sentences are logically equivalent to each other because the final column here, where underneath the main logical connectives, are identical to each other. So they both have true whenever both A and B are true. They both have true whenever A is true and F is false. They both have true whenever A is false and B is true. And they both have false whenever A and B are false. That means that these two sentences are logically equivalent. So again, we can use truth tables like this to determine whether sentences are going to be logically equivalent or not.